So this is my way of understanding your shell model, Klee. So the 3D world is expanding by Planck length layers, and then each layer can be thought as a frame of time. And there is a choice of freedom from frame to frame, guided by the empire, at least that's what I always think, empires of the past or the most adjacent past. So, but that's more of like a causality thing, like a, forward in time. The different choice gives different degrees of order of the frames, which determines the entropy or probability of efficiency of language. But I was thinking this idea can also be expanded to have the order or choice or empire influence both ways in time. So retro causality. So
in fractal theory, there's a concept that feels very analogous, which is a strange attractor. So you think about an evolving complex system, and it has a potential to evolve to some state of order, and that potential from the future acts as a strange attractor in an evolving fractal to pull the system forward towards its future its future determination.
Yeah. So anyway, so that's what I understand, and then I went to build this kind of picture to see, because I have to understand it very intuitively, visualize everything for me to be able to, carry it further. So this is a universe, start from the center, and each layer is a Planck length. Let's say Planck length now, but it's keep expanding outward. So then I give, this is like, for example, frame 0, frame 1, frame 2, so on. And if this is now, if we're in frame 6, then these would be the past and these would be the future. So that's the idea. And then I was thinking the effect of the empire of Fi goes both ways, the future and the past. Basically, if I'm now, okay, so we don't know the past, we don't know the future, but we know the now. So we are sure about the now. So this is something we have, and then the now would have its empire. So once we are certain of the now, and then there would be an empire that goes both directions, to the past and to the future. So that kind of like, in a way, all these nows can interact with each other, with their empires. And then that's how we can calculate maybe the entropy, the order.
And the probability for interaction, so it doesn't have to be deterministic.
So that's kind of like the kind of idea.
Yeah, that's a nice diagram.
Okay.
So then some part is deterministic, which is one which is imposed by the empire, and the other part
the
has
empire is
freedom.
not completely deterministic.
It can't be. It's not deterministic. Yeah,
even the empire itself, just the tile which
that's
are
a
in
part.
the
He's talking
the
about
part. Yes,
there's a one part is
deterministic and the other part is not.
Well, the thing is the empire itself is a choice. So, is it not?
The empire is
we will not have a choice on the empire. Only a choice on the syntactically free tiles.
The empire does not determine everything. The empire is just
only
a subset.
That's what I'm saying. Only the syntactically free tiles.
Yeah.
Yeah. Okay.
Oh, it's one view, but it's beautiful. Yes.
Yeah. Okay. So anyway, so that's a theoretical frame.
Fang, I have a question. So, is there any clean logic or clean kind of foundational formalism that would also allow the choice of the empire itself to be non-determined? In other words, obviously, as I build shell 2, I don't have to have that empire for shell 2. I can, if I want, choose the next empire, right? Or I don't.
Well, I'm just thinking, what is for sure there should be the emperor, and that should be have an empire. There is always certain part that you're sure, and that part that you're sure should have certain influence. Okay, so then of course you can have a freedom of what is sure. what part you pick to be
sure.
certain.
That's what I'm saying. You can if you want. From what I understand about the shells, you can either have an algorithm that is deterministic for each empire at each shell. That's my first thinking from learning about your window and empire window.
But it's not deterministic. The empire, I said that it can only determine certain past or certain future.
No,
but there's a lot of freedom also.
No, I'm saying I was saying we actually can build a model where the shell by shell empires are determined, the empires only. We can if we want to. Or
we cannot determine the whole next shell. That's something.
No, not at all.
Right.
Yeah.
Only part of it. Yeah.
Well, I'm trying to label here. We can create a model if we want, where the sequential ordering of the empires is determined. Empire 1, if you know Empire 1, then you know Empire 2, you know Empire, the empire in shell 2, shell 3. We can make it determined if we want. Or within the same basic types of formalism, we can, if we want, also have shell 2 have a different radius such that it has a different empire, a choice of empires.
No, but these empires are not all the same, because if we are in shell 6, shell 6 is certain things because we're sure about this now, and it has an empire to influence the future, but it only influences, for example, 40% of F7. And so then when you go to F7, only 40% of them are determined, and the other 60 are not. So then when you go to the F7, you have a variety of choices of what is F7, and it's of course depend on which one you choose, and then they're gonna give you different influence in the future. So there is never a determined like a frame by frame empire determined. I don't really understand.
Okay, if I go to shell 2, the logical first simple model is to say at shell 2, my next shell is at some radius, and so I place it at that radius, and I place my empire window to be coincident with a set of points or tetrahedra or 20 groups that's at the center of the empire window, at that prescribed radius for shell 2. Then I can move my my projection window around up to the boundary.
Yeah, that's what I'm saying, the freedom.
That's idea 1. So in that idea, I hope I was clear that the position of that projection ring is centered upon the empire, and you knew, even when you were at shell 1, you knew the radius of the center of that empire window.
But it does not have to be centered, because this cotton window, as long as the empire window is inside.
The empire window. That's why I have to list. I'm being very, very precise. The empire window can be determined at shell 2 because you decide in your algorithm, I'm going to put it at X distance is the next step for the next shell, and the empire window must be centered on some set of points or tetrahedra. And that can be determined if you want it to be. If you want to determine the coordinate of where your next shell is going to be as far as the empire window center, then you have the ability to move around the cut window. I
don't think there's a concept of an empire window center. What I'm saying is
there's not?
Whatever that is decided, gonna decide the empire window. I mean, for example, if there is 2 points or 3 points are decided, then and we know the projection window should be in this direction, then these 3 points would decide the empire window to be like this. And if, for example, these 2 points are decided, then the empire window would be like this. So there is not a central idea. It's really like what you're sure of determines the size of the window or the position of the window.
Okay.
Yeah.
So it's kind of Anyway, that's kind of neat because it's partly deterministic and partly causal and partly non-causal.
So it's an implementation of the third ontology, the code theoretic axiom.
Yeah, right.
Yeah, exactly.
Yeah.
This is what that is. Okay, so the methodology. So first I have already done a demo with the Ammann tiling, which is in 3D, And then, I did the animation on the shelling, and what I'm gonna show in a moment. And the next step I wanted to do is a corrugated layer projection of the alpha-epsilon quasicrystal 3D, and I will model on animation, and then also, to compare the degree of ordering. There are a variety of ways of kind of doing that, and then I actually wanted to start with the empires, like I said, the empires in alpha-epsilon quasicrystal, and then project to 3D. So right now, I think that's, I tried to insert this, but it wasn't successful. And I'm gonna show the video. Okay. So you can see, from the first layer, each time I just added another layer. And then if you look kind of from the outside, you literally see the kind of a Phazon flip almost. Like it gives you an illusion of a 2D, but there is Phazon flip in 2D. So if we go all the way back.
Yeah, I remember you sent me this. I was really impressed with this. So Fang, what's going on right there? There's an addition of a layer,
yes.
right? But
yeah,
we're
so
just
compared
seeing it
with the
2D.
original layer, there's just another layer added. But look at this, and then the next three, they just form a complete cube. It's like you're seeing one half of the cube, and then now you're seeing the other half. But this just like these two halves actually make the Phazon flip.
Right.
In the projection, yeah, I see it.
Yeah. But not all.
But really, in this picture, nothing's flipping. We're just adding more rhombohedrons.
See this one, right? That is a Phazon flip.
Yes, this is the addition of a cube.
Because I'm just kind of trying to have some sense of, how are you gonna see the dynamics if you just keep adding frozen layers? How are you gonna recognize what is the order and what is less ordered, what's more ordered, right?
Yeah.
So that's why I'm looking at these, and maybe these would give us a clue of what's the meaningful order.
I think from the results I'm getting, the Phazon flips and the 3D tilings occur on planes.
Yeah.
Like whole planes at a time will, like all the tiles in a planar region will flip at once.
Oh yeah, that's right.
So yeah, in the Penrose it was these ribbons that flipped.
Yes. Yeah, it's a whole ribbon.
So
and
it's
here's a whole layer.
Yeah.
Okay, interesting. Yeah, see, you can see these, Klee, all the 5 that are flipping.
So when you say planes, you mean like you'd have 1, 2, 3, you'd have some number of planes that the changes on the outside
Look
of
at it
this
here.
growing.
Look at it here, Klee. This. There are 5 of them, right? They are on one plane, like there is a cone, like
that's what I'm
dipping
saying.
down.
Yeah, I get
and then
it.
the next frame, boom, you get that there's another layer covered
changes on another
top.
plane.
Yes.
But you'd have multiple planes. In other words, it'd be one here, one here, one here.
That's why in 2D, you have these ribbons all wiggling like that way, and the next is wiggling the other way. It's kind of the same thing, which I'm gonna okay, so this is about it. I haven't done any further on this.
So does everybody in looking at this kind of understand the idea of the action horizon? It's a very crazy idea. It's the idea that when you ask, where are you? Where are we now in the expansion of the universe from the Big Bang? Well, we know that in the time domain where we are, right? We're in the time domain at about 14 billion years after the Big Bang. And we know that in the time domain, if we look at it with QGR modeling, we know that the time domain is discretized. And we probably want to discretize it with shells because we want to have a cosmological thinking. So that means time-wise, we are on the very, from your vantage point right now, we're on a shell on the action horizon that is the very last shell, right? But if you look from another vantage point in your future, it would be another shell at a greater radius from the Big Bang. But it's a weird idea because these shells are playing at 10 to the 44 shells per second that you experience 1 second. 10 to the 44 of these happen. And the shells here are of thickness. So they're Planck scale, but they are of some thickness. And the question is, for you, do you see abstractly how all action, right, of time here where you are at 13 billion years worth of shells, where there was 10 to the 44 every second over those 13 billion years, where all the particle actions, and now, by the way, we're on a shell that from our vantage point is virtually flat, right? It's spherical, but the radius of the universe from the Big Bang is now 15, because right now the diameter of the universe is estimated at 33 billion light years, even though the whole universe is only 14 billion light years. So the shells are, from our vantage point, are so vast that you might as well think of them as flat. So, and if you're thinking of it as flat, think of yourself and your life and us playing on a three-dimensional video monitor, where one frame is just a three-dimensional thing, but the TV monitor, the 3D TV monitor looks like this. It's going through these shells on the action horizon, and because they're 10 to the 44 per second, you perceive everything, right? Because just to perceive the full length of my body, it's many, many Planck thicknesses, but they're 10 to the 44. So my question is there something broken in my thinking where I'm saying that our 3D reality here could possibly being it's similar in a weird way to the strangeness of the holographic principle, but it's different than that. But it's this idea that a 3D television monitor that moves very, very fast creates a large volume of action for you because of the 10 to the 44 Planck scale shells. And there may be some illusion going on here where in the classic view we would think, oh, well, there was this big bang and space is expanding, but I can be a pattern that's deep inside the volume of this sphere that's expanding, and I'm moving around down here. But this model that I'm suggesting is radically different than that. This says that all your action is happening on this ultra-fast 3D monitor that's at the action horizon of the expansion of time. So I just want to make sure everybody understands that because it's such an abstract thought.
Basically, each frame is a two-dimensional thing.
No, each frame is a three-dimensional thing, so it's very...
Well, it's Planck length thickness.
Yeah.
So that's kind of like a 2D.
Well, no, it's a very small thickness, but it's not a two-dimensional thickness. It's an idea actually...
It's like, for example, our body, right now I'm instantly seeing myself here, but what you're saying is actually my body was cut into different frames.
Yeah.
And so...
But not 2D, just of a very, very small...
Well, I mean, it's almost like
virtually,
2D to me.
Virtually.
So you're saying, okay, so 10 to the 44 frames. So what's the Planck length? 10 to the how many? 10 to the
10
third?
to the negative 33? 34?
10 to the next is 34?
4.
That's a Planck constant.
Of a meter. No, it's the Planck...
Planck time.
The
10
Planck,
to
no, the
minus
Planck length
34.
is 10 to the
You
negative...
want Planck length 10 to the minus 35 meter.
Okay, so 10 to the minus...
35?
Okay, so we have...
35?
Okay, so then we have a 10 to the 44 frame. And each frames is 10 to the...
35?
Minus 35 meter, right?
Yeah.
So then multiply together, that's 10 to the 9th meter.
Yeah.
So basically we're talking about each second there is 10 to the 9th meter of the expansion of the horizon.
Yeah.
So yeah, each second I guess, then that means this is a nanosecond, each nanosecond I see 1 meter.
Mm-hmm.
I don't know if that's gonna be good enough.
Maybe
because we can measure we can even measure femtosecond. So anyway, But now we understand the idea. So can I move on to the other one?
Oh, but Fang, we haven't decided what the distance between shells is. Everything's conceptual. There may be a scaling algorithm where...
No, I'm just looking whatever your assumption right now.
Yeah, but there could be a scaling algorithm where the shells of some thickness could have a Fibonacci pattern where they get further and further apart in distance as it expands outwards. Like, we don't know any of those questions yet.